We have already mentioned the following two slides, the earlier review meeting. It simply shows the rate in which the algae grows and the model we have found to feed the mussels. With the toxicity test we have taken of the wiring and the pipes for about 30 minutes, no toxic leaching detected. Algae counts continued rising, confirming materials are safe, which brings us to the ammonia test. Pooled group data show total ammonia rises with mussel biomass, but micrograms NH3 gram when mussel falls at higher weight. 10 grams mussels produced no detectable NH3 in 1 hour, likely low excretion or assay limit, implying metabolism scales nonlinearly with size or density. This brings us to the mussel test, in which we test their behavior at different water temperatures. At 19 degrees Celsius optimal, mussels filter efficiently, high algae removal, frequent shell opening. At 22 degrees Celsius ambient, thermal stress causes more shell closures, lower filtration, and higher residual algae. Highlights need to maintain preference less 19 degrees Celsius for peak biofiltration. The feeding, based off of the system, in which our system was pumping 20 liters per hour between the mussel and algae bucket. And because of that, we have to adjust for that to find the most optimal algae concentration, which is shown on the slide.
OD sensor readings have been taken a day apart. As we are using a blue LED, the RGB sensor detects the blue light the strongest. We observed that the starting concentration of the RGB final reading is lower compared to the RGB initial, meaning that there's lower light absorbance in the OD sensor, indicating an increase in algae concentration. Both readings are stable, showing fine-tuning of the OD sensor.
To tune the PID controller for our temperature regulation system, we used a method based on system identification, specifically the first order plus dead time model, also known as FOPDT, combined with the Ziegler-Nichols open-loop tuning approach. We began by applying a full-step input to the cooling system. That means 100% PWM power, and logged the temperature every 5 seconds for 20 minutes. From this step response curve, we analyzed how the system behaved. Using the data, we identified 3 key parameters. First, L, the time delay before the cooling began to affect the system, was measured as 20 seconds. Second, tau, the time constant, was found to be 533 seconds. And third, K, the system's steady-state gain, was calculated by dividing the total temperature drop by the input step, which gave us a value of 9.74. Next, we applied the Ziegler-Nichols tuning rules for PID controllers using these parameters. After plugging in the values, we calculated our initial PID parameters. The results were P equals 6.9. I equals 0.15, and D equals 76.2.
For the web page, we used it to tune the PID values while also getting RGB and temperature readings. We also added a slider to adjust the pump speed manually when needed.
On the left are 2 code snippets. The top saves thermistor readings to a CSV file, while the bottom scales the PWM to ensure each pump operates above its minimum required level.
We tested the performance of our siphon system, specifically using 2 pipes at once to analyze the flow. This graph shows the flow rate over time, while the measurements fluctuate from moment to moment. If you look at the overall data, you can see a clear, gradual downwards trend. This is expected as the water level drops. This result confirms that our siphon design is more than sufficient to power the system.
By experimenting, we found a correlation between PWM and flow rate Q. We ran full experiment and got PWM versus time data, see the plot. Using the correlation, we found Q and then determined the power. Using Python, we used the time and the now known power to determine the total energy, which turned out to be 88 joules.
So the key question is, how much energy did we actually save? We found that the rate of energy loss is directly shown by the slope of our cooling curves. The uninsulated setup cooled at a rate of 0.0003, while the insulated one was slower at 0.0002. By comparing these 2 rates, we calculated a total energy saving of 33%. This clearly shows how effective sand is as an insulator in our experiment.
This is the final setup used to test the complete system. It illustrates the sand acting as an insulating layer between the mussel bucket and the plastic bag, the individual electronic components, and the implementation of the siphon.